Hello, we are going to see the question from GATE. We are going to see the question from GATE 2014 here, ECE paper from the signals and system subject. Here, let H of t denote the impulse response of a causal system with the transfer function 1 by s plus 1. Consider the following three statements. S1 equals to the system is stable. S2 equals to S2 is h of t plus 1 divided by h of t is independent of t for t greater than 0, and S3, the statement S3 is given as a non-causal system with the same transfer function is stable. So for the above system, we need to decide which statements are true here. So coming to the first solution of this one, coming to the statement 1 here, that is the system is stable. So given that h of t is a impulse response of a causal system, nothing but this is the transfer function of the causal system. So h of s is given as 1 by s plus 1. So this is the causal system it was given. So calculating the so so causal system is nothing but by calculating the inverse Laplace transform for this, we will get this as h of t equals to e power minus t u of t. So u of t is nothing but that exists only on the positive time axis. There is no values on the negative time axis. So the system is causal here. So causal system. So for this h of t, by calculating the transfer function, we will get it as h of s equals to 1 by s plus 1 with an ROC of real part of s is greater than minus 1. So real part of s is greater than minus 1, and by taking this on the s plane, so this is minus 1. So real part of s is, this is s plane. So real part of s is greater than minus 1, nothing but this is the ROC here. So we can observe that the ROC includes the j omega axis, nothing but the system is stable. And this we can observe that this is the pole minus 1, this is the most this is the pole of the system. So the ROC lies on the right half of the most pole value. So the system is causal. So we have the condition the system is causal, and the ROC includes the j omega axis. So the system is stable itself. Otherwise we can also verify by using the expression integral minus infinity to infinity mod h of t value must be less than infinity. By observing this, it will satisfy for this h of t. So the system is stable. So we can say that the statement s1 is true here. The statement s1 is true here. So coming to the second statement, that is s2 equals to h of t plus 1 divided by h of t is independent of t for t greater than 0. So considering the second statement here, s2, that is h of t plus 1 divided by h of t, we need to calculate this one. So we already calculated the h of t, that is we have the h of t equals to e power minus t u of t. So h of t plus 1 is nothing but this is e power minus of t plus 1 into u of t plus 1 divided by this is e power minus t u of t. By simplifying this, we'll get this as e power minus t into e power minus 1 u of t t plus 1 divided by e power minus t into u of t. So e power minus t will get cancelled, and this becomes u of t plus 1 divided by e of e into u of t. So here we can observe that u of t plus 1, u of t plus 1 is nothing but the t values are greater than minus 1. U of t plus 1, you can observe that here u of t plus 1 is equals to 1 for t greater than minus 1, and u of t equals to 1 for t greater than 0. Now we can see that in this expression, we got the we got uh, we got this h of t plus 1 divided by h of t equals to, we got it as 1 by e itself. For here it is t greater than minus 1 and t greater than 0. T greater than 0 is nothing but that is obviously greater than minus 1, that is nothing but t greater than 0. Here we can observe the statement S2. This is h of t plus 1 divided by h of t is independent of t for t greater than 0. We can observe that this value we got it as 1 by e, nothing but that is independent of t itself for t greater than 0. Nothing but the statement S2 is also true here. The statement S2 is also true. Coming to the S3. Coming to the statement S3. Statement S3 here. So here given that the statement S3 is given that a non-causal system with the same transfer function is stable. So given that the system is causal, here the statement 3 is taken as a non-causal system with the same transfer function. With the same transfer function is stable. So taking the same transfer function h of s equals to 1 by s plus 1, considering that the system is non-causal. Considering that the system is non-causal here. So by calculating the inverse Laplace transform for the non-causal system, considering the system is non-causal, we will get that h of t equals to e power minus t, but this is u of minus t will get, that is the non-causal one, that is the non-causal system. And for this the region of convergence, by calculating the ROC, we will get it as real part of s is less than minus 1 will get. Real part of s less than minus 1 will get. So by taking the by indicating this on the s plane, indicating this on the s plane here. So by taking the s plane, we have the pole at minus 1, and we have the ROC. We have the ROC is less than minus 1. ROC is less than minus 1. So ROC is less than minus 1 is nothing but we can observe that this is the j omega axis. So the j omega axis, the ROC does not include the j omega axis. So here we can observe that ROC not including j omega axis, nothing but we can say that this is unstable. So stable is nothing but it has to include the j omega axis, and we can have the ROC is left half of the pole, left half of the most significant pole here, then the system is non-causal. So for causal system it should be on the right half of the most significant pole. So but it is left, so the system is non-causal. That's what we consider here. So the same transfer function with the system is non-causal is an unstable system. So what is given here? A non-causal system with the same transfer function is stable is given. So the statement 3 is false here. So out of the given three statements, S2 is true and S1 is also true. So the option out of the four options, S1 and S2 are true. Option A is the correct answer.